Okay, welcome back. Again, this is our Calculus 3 class notes. Now we are looking at page, let's see, what page are we on? We're on page 20. And we're working in section 12.5, which is lines and planes in space. And we're now dealing with planes. So just like we learned how to find the distance from a point to a line that's in space, we also want to find the distance from a point to a plane that is in space. So here's how we're going to do that, right? If P is a point on a plane with normal n, so here's a plane, okay? P is on the plane, okay? Then it has a normal vector. Now we want the distance that this point S is down to the plane, a perpendicular distance. But the best way to do that is to take the projection of this vector PS onto the vector n, right? That would be this vector right here. And then this distance, which is the length of the projection of PS onto the vector n, would be how far this point is from the plane. Okay, so how do I find the projection of any vector onto another vector, right? It's the dot product of the two vectors divided by the length of n squared, the vector we're projecting onto, times n, the vector, because it'll be a scalar multiple of n. So if I simplify that, think of these lengths as absolute values. So I have that length of n and divided by the length of n squared. That cancels out one of them here and this guy. So I get the absolute value. Distance is the absolute value of the dot product of PS dot n divided by the length of n. So it's a nice tight formula. So as example 22. We want to find the distance from the point S, which has coordinates 1, 1, 3, to the plane 3x plus 2y plus 6z equals 6. So there's a component simplified equation for that plane, which we can immediately see the normal to the plane then is the vector 3, 2, 6, right? Okay, so finding any point P in the plane doesn't matter. We need an x, y, z that satisfy this equation. The easiest thing to do is to find an intercept. So we'll let z equals 0. That tells us that x has to be 2. So the point 2, 0, 0 is in that plane. So this is our point P. So what we want, the distance then, is the absolute value of PS dot n divided by the length of n. Okay, so the vector PS, terminal point S, initial point P. So 1 minus 2 is minus 1. 1 minus 0 is 1, 3 minus 0 is 3. So the vector PS is minus 1, 1, 3. I'm going to dot that with our normal vector, which is 3, 2, 6. And then divide it by the length of our normal vector, 3, 2, 6. So when I take the dot product, I get minus 3 plus 2 plus 18, right? Remember, minus 1 times 3 plus 1 times 2 plus 3 times 6. Divide that by the length of the vector 3, 2, 6, our normal vector, which is the square root of 3 squared plus 2 squared plus 6 squared. This all simplifies to 17/7. So the distance that the point S, which has coordinates 1, 1, 3, is to the plane is 17/7. Now, another thing that we'll need to do in the future is be able to find the angles between planes. So how do I find the angle between two intersecting planes? Okay, when we talk about the angle between two planes, we're talking about the acute angle between their two normal vectors, right? That's the easiest way to find the angle between two planes. So I try to be very careful here and draw something that looks like two planes intersecting. So this is plane 1, I'm calling it. This guy is plane 2. And they intersect. Planes will intersect in a line. So this is the line that intersects them. So this N1 here is the normal coming up out of plane 1, and this N2 is the normal coming up out of plane 2. We want the angle between those two vectors. Well, we know that the dot product gives us the cosine of the angle between any two vectors. Specifically, the cosine of theta, the angle between two vectors, is N1 dot N2 divided by the length of N1 times the length of N2. Okay, so in other words, theta then is the inverse cosine of this value. So let's find the angle between the planes. 3x minus 6y minus 2z equals 15, and 2x plus y minus 2z equals 5. So we can quickly see, let's call this guy plane 1, this guy plane 2. It doesn't matter what you call them, but this guy quickly has a normal vector of 3, minus 6, minus 2, and this one quickly has a normal vector of 2, 1, minus 2. So it's just mechanical, right? Cosine of theta equals the dot product of those two vectors divided by their lengths multiplied, work it all out, and you get 4/21. Theta then is the inverse cosine of 4/21. So if you want radians, it's 1.379 radians, or if you want degrees, it's 79.019 degrees.